All right. Well, welcome everyone to our RChain Education session for today, Tuesday, June 9th. And today we're going to be discussing, oh, Jim has arrived. Hey, Jim, welcome.
Hi, Jim.
I went ahead and pressed the record button, so taken care of. You can take the day off today. Today we're going to be discussing monads, an introduction to monads. And Tomislav, you can take it away.
Okay, so for today, I said we can talk about monads, but maybe we can first start from something simpler, and then we can see why we really need monads. So I was thinking how to introduce this, and I was thinking to start with just simple type, right? Simple class as a box, as a container, and this is usually this is like ID container, or if we don't have any additional functions, this is just like a box, right? When we want to construct some value, we can just put it in the box, right? And we can extract this value out, and we can do this in two ways in Scala, right? We can say v1 like value 1. We can say b1.x, because this x is just a field, so we're just taking the value. And we can also deconstruct this value as using this constructor. This is why this is a case class, because we have only one case. We have only one constructor. So we can say, oh, this is a value v1, and we want to deconstruct this box b1. So maybe this syntax can be a little confusing, right? How this works, right? We are using constructor on the left hand side. So this is like in position of deconstructing. We are saying, oh, if something is constructed in this way, this v1 will be x. So when we can print this v1, and this should be the value that we put in here in this box, right? Does this make sense? That this kind of expression is really the same as this one. We just want to extract whatever is in x inside this box.
Yeah, I can follow the basic idea.
This is similar to pattern matching from what I remember in Rholang.
Yes, exactly. This is completely the same. And we can use matching. We can say, oh, we will match B1 with this case. And in this case, we will return V1. So I probably need to do this, or I always forgot on which order is match. This is case, and we need to write case. So this is the same syntax for this expression. We are matching B1 on whatever constructor this object has, and this object has only one constructor. For example, if we have option type, so let's write So we have multiple ways how can we construct this option type. But let's use extension function in cats. So we want to import all of the syntax. So we have available this extension on option type. So this is the option of integer, and we can do the same matching. We can say this option value we can match on some value, or we can match on the none case. So here we need to return something, so we can return, for example, 0. So this is the option. So basically, if you remember what is an option type, it is it can be constructed with two classes, with sum and none, right? We have sum, which is very, very similar to box. It only has one value that you can put inside. And there is a class none or object, because there is no input parameter. This is another class that we can construct for this base class option. So when we are matching, on this object option, we really need to cover all of the cases that is possible to create this option type. And this is what we are doing here also. And because this box is simpler than option type, it has only one case, and we can write it in this way. So we are compacting all, this match to be like a very simple match, just one case. Here is the box, whatever is inside binds to this variable v1. Is this make sense? How this match has a nicer syntax if we are matching something very, very simple.
So is this also is this something else besides you have a value that could be undefined, so you could say, well, it's an option of either string or undefined.
You mean
how is this different from that?
You mean from a box, or?
Well, from any value that can be of type T, or it can be undefined.
Oh, so what is the type of this O1? This is option of integer. So it is not just the value. It is packaged up in this option type. So the value is inside this class option. So we cannot just access the value because in one case we really have the value inside, but in another case we don't have value. So if we are just directly accessing the value, we can have this case, as you said, that there is no value. So in this matching, we are just providing for this case of missing value. So we are saying, oh, if this is the case where we don't have value, we will supply something like a default.
Just relating it to other languages. I mean, where you don't have a value, that would be like, undefined, right? Like
null, yeah. But because like null or undefined, it's not always visible from the type if this is possible or not, right? So now, for example, in C#, there is like integer and nullable integer. So they have this kind of notion of possibility that you don't have a value, right? But yeah, this is like, the box is the most simplest class with just one case, and then option is like first a little complicated with two available options, two available cases with value inside, or if you don't have. So this is like an introduction for just the syntax in Scala and what we have with this class. So we are working with something that is inside this class. We can see how this works with option, how it works with box. So now we can say that, yeah, this box is something special for us. You know, whatever is inside, we want to work on this value, what is inside. And we want to write functions over this box, right? So maybe with box, as this simple is not so obvious why we want to do this, but we can see this, and we can imagine for option type, this can be much more usable. Because if you always need to match for both cases, then this is like very, you always deconstructing, do I have a value? Not, I will do something. So in each function call. So this is what we want to avoid. So let's first write function that Greg also mentioned in his lecture about monadic design patterns from the web. The map. This is a factorial part. This is just a functor, right? We want to be able to change the value inside box. So let's write this map function. So we have whatever is in A, we want to this another type to be returned, and we can say the first argument is the box, and whatever A we have in this box, and the second argument can be a function from A to this B. And we can write this down. How can we apply this F inside box? So we need to first deconstruct whatever is inside box B. So let's write full expression. So we are matching on this B, and we have only one case, and we have this value what is inside, and we will just apply this function to this value. But we want to return the box with B inside. So we will put everything inside box. So what we did, we unpack value inside box, this value v1, and apply this to a function f that we have for this mapping. And we are package up this again inside the box. So is this function like clear? There is no magic. We're just unpacking the value, applying the function, and returning back in the box. So our value from box A, we are moving to box B. This is the functor. When we can transform, when we can, so the right definition of functor is we can move this function from A to B to a function from box A to box B. So someone give us A to B, and we really have the function from box A to box B. because this map is accepting this A to B, and the whole map is box A to box B. So we are like moving from A to B to box A to box B.
Yeah, I'm actually able to follow along after reviewing the category theories series of education videos. So you're speaking in the same language as category theory. So
yeah, exactly, yeah. So what we can do with this function map? We can transform whatever is inside box, and so we can have function plus 100, where we're accepting some integer, and we can return something inside this integer also, but we are increasing whatever is inside. So we are putting this inside the box, and we are saying just I plus 100. So we are just updating the value inside the box. So this is usually, I didn't want to immediately go to box. First, I want to just increase the value. So this is just a normal function from integer to integer, right? This is first what I would like to map on this B1. So now we have a map. We have a B1 box, and we have this plus 100 function. So now we just changed the value inside the box. So we really did this mapping of B1 to change the value inside, and now we have the box with different value. And this is how we are like moving. We are just composing multiple functions, and we are creating the next values. For example, B3, we can do the same thing. But we can map B2 and apply the same function. So we are doing plus 100 two times. There is also nothing strange here. Just using this map function as higher order function to accept another function, so we can apply it to whatever is inside the box, right? Can I go further?
At some point, will you show us how you would add the constraint that the integer for the map must be a positive number?
You mean, for example, to modify this plus 100?
No, to modify the map, to say that the function map can only operate on positive numbers.
So the question is where we want to introduce this kind of constraint.
Yeah.
So with the box.
I'll tell you why I'm asking it is because, in C#, for example, there's every time you call a method, you've got all these contracts that you say it must be greater than 0, strings must be null, all that type of stuff. And I'm not seeing a lot of that in Rholang code, and in RChain code, and I'm not sure if that's intentional or not, because it cuts down on your unit tests.
So with just a box, we don't have a way to specify some other case, right? But we can talk about the option type, where and this is where I want to go. But I just wanted to first to show just with the box. But
okay.
it really even more is visible with option type with two cases.
Okay.
So this is something that can be this constraint can be with this maybe divide function.
Yeah. Mm-hmm.
Where it's important that we are not dividing with 0,
Mm-hmm.
right?
Mm-hmm.
So the box. So in the case of box, if we are just returning a box, so we can say, okay, if I equals to 0, and now the question is, we only have box, so what to do? I mean, we can always say, oh yeah, return 0, but maybe we want to push this on the type level. So maybe we want to return like option type, which case two cases. So we can say, oh, if this is 0, we will return none because we cannot divide with 0, right?
Mm-hmm. Okay.
And if we have if we have something that is not 0, we can divide with I don't know, 100 with I, and we can put this inside the option type. Right.
Okay.
And so now we are not working in box. We have this option type. So let's write some option that is our option value. Let's be just anything. Maybe we can have multiple values, but let's do this one. So let's also write map for the option type. So this is functor for option type. And it's really completely the same. We need to cover all of the constructors. And we need to say how this mapping works. So I will write in two different ways just to show that both of this is the same. And for none case, we are returning none. So now we have a way to match whatever we have on our input argument, and we can say, oh, if we have none, then we cannot apply the function a to b because we don't have a. This option is empty. So we will just keep applying function f and we will return none. So this kind of function is totally normal, right? We're just matching on all of the possible cases for this type that we are receiving, and we are doing operations that when we have a value. But the point of a functor, to have a functor, is not to write this on every function, right? The point is we want to write this only once and then use this map to construct all the functions that we are using in our program, because we know how to match cases when we have a value and not. So why to write all of this matching in all of the places that we care about? We just want to have we just want to combine our functions, and at the end, if all our functions was returning a value, the whole expression will have a value. But if in any place where our function will return none, we will just stop execution and just say, oh, the whole expression is none. And this is exactly what I want to show. So let's start from creating option 2 value, and we will say, so what I have here, map, I need option 1, and I will create a function, no, I have a function, divide. So if I execute this, I think it's want to apply different map here. Okay. And so now situation is clear. So let's first apply what we have for this plus 100. With plus 100, I will call this option 3. So with plus 100, we just have the value inside option, this some constructor, and we increased the value inside. But in another case, when this divide also return option, we have this situation where we have sum inside sum of the value inside. So now we have the nested type as a result. So what can we do? I mean, do we know the result of this? What is possible from this value? How can we get rid of this one constructor? We have a value inside, and we can really write this function down. We can say, oh, we really need this function, right? So we need something that will, let's not just not name it. We have the first, we have this option that has this type. This is inside, this A. So this A can be whatever we want. And we have outside option. And we want to convert this to option just of A. So we can just match on this input option. So what we will return here. So we have, what is V1? V1 is whatever is inside this option. And whatever is inside this option is another option. So we can just return this option, whatever is inside. And for none case, we will just return none. So we really see that this function, which is usually called join, it's just doing exactly the same thing. It's matching on the constructor, and whatever is inside, we are just returning. So it's really, for option type, this is very, very straightforward. Because if we have a value inside the option, we can just return this option value. We are just like removing one layer outside. And this really tells us we can remove any number of options outside. We can just flatten the result. And this join function is really what makes a monad. So this is a way how can we flatten out whatever whatever object we have. Like if we have a box of box, this is also very simple. We will just extract the box inside and return the box. Or if we have a list of lists, we can just extract the list inside and put this in one list. So now the question is, but usually we don't see this join. This join function is usually not used in most of the languages directly. We have different kind of function. And this function that we usually have is very similar to this map, function. And it's usually called flat map. And the only difference is that we are not returning B from this supplied function, but we are returning whatever container we have. So we are returning option of B in this case. And we can do the same implementation. We can say, oh, we have a value inside. We will just apply this value. And for none case, we are just returning none. And we have implementation for a monad for option type.
Quick question. So the flat map can be applied to the monad, but where you have F, then F is option B. So can flat map be applied to the functor as well?
Yes, there is a relation. Every monad is a functor.
Oh, okay. Go ahead.
And this is visible because it's almost the same. The only difference is that this function that we are composing is returning this in our container. And there is a relationship between the flat map and how can we get the map from flat map. So for example, so let's define one function that is also very useful, and it is defined in Scala, but it's so simple that we can write it down. And I was using it in my examples already. And this is identity function. Just like this. So we are whatever we have as an argument, we are just returning the same thing. So it's really from category theory. This is also important thing, because you can say, oh, this A that we are receiving as input is the same as returning type. This is identity.
Right, that was one of the properties of a monad or a category, is the ability to have an ID.
Yeah. And I'm writing this function down because I want to write a relation between join and flat map. So and functor also. So join, let's call it one. We can write join so we have option of option. We can apply, and from our flat map function, we already see how can we use it. So we can say flat map of this option of option, like nested option, and for this transforming function, we will just return ID. Because we are saying maybe Scala needs this. Okay. So Scala don't want to accept just this as a first-class function. I need to use this additional syntax to say, oh, this will be the argument that I'm supplying. Although IntelliJ is saying, oh, you can convert this to a method and just return it. So this is like confusing when IntelliJ is telling you something that Scala doesn't accept. But I'm just using this identity function as this function, right? So when this flat map gets this option of option, this V1 will be option, this inner option, and this F will be identity. So this means it will just return whatever is inside. It will not do any transformation. So this is how we can define join just with the flat map and identity function.
So, so I understand a monad, in order to be a monad, it has to have identity. So monad A is, has identity A, but I guess I'm confused that a functor has identity as well. And to me, it looks like you're using the identity of the monad A to represent the identity of the functor.
So in this case, the A is the inner object. A is not the monad.
Okay.
The monad is this box.
Oh, okay.
A monad
in this case,
is
the option type. A monad is a functor, but this A, for A, we didn't say anything. A can be whatever.
Oh.
We don't have any
Okay.
clue what is A.
And I'm getting confused with monad and monoid. So, right, okay. So that's where my category theory is getting me confused. So, yeah, I was thinking monoid, but I need to think. So a monad is a function. Okay.
Yes, and I want to talk about monoid also. In the same way as Greg is using the notation here. Oops. He's talking about different properties, and I want to go to the same thing. So Greg is comparing monoid with monad, and the same structure here is completely the same as Greg was explaining on the latest Casper session. If you remember yesterday, he was exactly wrote the same monoid construction. So today, this introduction to monads is not over, right? I want to go back to monoid and compare this to monad, so that we can see, what are the difference, how they're related, and I want to show how this is very very connected to Greg's lecture before, but also what Greg is talking today with the ladle and operational semantics in the logical form.
So I guess I'm getting confused with the semantics, and maybe if I break it down into most simple terms of object, I know what an object is, and a function, I know what a function is. If you have two objects, object A and object B, they're connected together with function f. So is monad and monoid, are they equivalent in some regards to objects, and functor is still roughly equivalent to a function? Am I still on the right path there, or do I even have that confused?
No, you're on the right track.
Okay.
So in this case, we are talking about option as our category, and the objects are A.
Okay.
So we have a functor from different objects in our category. So we are working in the option category. Everything is happening in the option category, and we have different functions from integer to strings or whatever we have inside this option in our option category, right?
And just to clarify, so if A is an object in a category, that's category A, and then we have a separate category, a separate object in a separate category, object B. In order to make this transformation, we're going from object A in category A to object B in category B with the functor or the function. That's the process or the method that's being connected. Okay.
The only thing is important, but if there are different categories, then we have a problem.
If they're in different categories, so these have to be within the same category. Okay, that was
because you are saying, for example, I have option and I want to move to box.
Okay.
This is this is not a factor because you're moving to different categories, and if we are changing categories, this is called a natural transformation.
No, okay.
So we can, and this is why Greg is talking about naturality.
Okay, now it's okay. So
yes.
So we're all of what you're explaining is that option, or it's all within one. All this activity is happening within a singular category. It's not from one category to another. It's all contained, self-contained in one category. A to B is in one category.
Yes.
Okay.
If we can move between categories, we have this natural transformation.
Natural transformation. Okay. It's these important details I'm forgetting from category theory. So yeah, that was helpful.
Yeah, and I want to go into details how this natural transformation are expressed, for example, in Scala, right? Okay. How we are moving from one this box to another. Yeah.
Okay.
So I wanted to, I wanted to also to go into other direction to implement a flat map with join and functor. Maybe you can help me, how this can be implemented if someone has some idea. So we are doing the same thing. And so we want to use a join that we already have, and we want to use our functor. So let's map over this B that we have, and if we map over this F, this will be the problem because we have this nesting. We seen this previously, right? We are mapping something that is returning in the box. So we have option nested option, and we know what to do because we have function to flatten the nesting. So we will just call join here for the whole expression, and we are done. And this is exactly how flat map is created from a join of a monad and from the map of the functor. And this is the most used function currently for using promise or whatever. You know, you will always use this flat map. So the whole story of monad is this collapsing. This is the, and yeah, I have one image for that. So we are now talking about this upper operations, right? From nesting of this M is like our option. So from nesting nesting boxes to just one nesting. This is our join, right? We are going into this direction and back. So a co-monad is doing this another part. So monad is collapsing or create or putting the value inside, and we see previously that this pure is really coming from applicative functor. But it's also because the monad is also applicative functor, we have this pure as part of the monad. And there is this another side where we can just duplicate, we can create nesting, or we can just extract this last box and we can get the value, which is not possible for an option type, right? If we have option of A, we cannot just say, oh, I will take the value. What if we don't have a value? So we cannot define extract for option type. Option type is a monad, but it's not co-monad because we cannot extract the value always. But for our box, we can do this, right? Because we can always extract the value. So we can define co-monad and monad for our box.
Okay, that's great. The term flat map, I heard it a lot, but now it's great to have an explanation about why it exists and how it works.
I started this in TypeScript, but now I'm thinking that maybe now that you mentioned the flat map, I want to show this with promise, because with promise this is not in JavaScript. This is not directly visible, because in promise then has two purposes. It has two implementation for map and also for flat map. So there is one name for map and flat map, and this works automatically. You don't need to say, oh, I'm mapping, I'm flat mapping. You just say, oh, I have promise, then I'm doing something, and this works like automatically. So what is doing now? Oh, so let's define our async function, because we want to work in promise. So P1 we can do something also very simple. We can just return x plus 100. So let's this be plus 100. But p as a promise, and we will have like simple one without promise, like just plus 100. So now we can have our function. Well, let me define in the same way, to not be confusing. Let it be main. So when we JavaScript, when we say async, we are saying that the whole function is wrapped in promise. So we have a syntax to describe this like special box, this asynchronous box, this promise. And here we can do, we can just use our function to get the value. And oh, we want to display something. For example, so I want to create this result, applying this main function. Let me simplify a little. Just with the initial promise. This is our value. So this is our first result. This is our second result. When we are using the promise and without promise. And I need to write this to a log to be visible. And let be just simple array. Let's see if I made some mistake. So I'm using now I need to specify some types, probably. Okay. Yeah, I'm not using main. So this val is just our initial value inside promise. And this is resolved immediately. And I cannot write this. Okay, this is not valid constructor, so
I think it's promise.resolve.
oh yeah, you're right. I was wondering which constructor is like shorthand for this case. So this resolve constructor is shorthand to not write the resolve function. So we are just supplying the value. We are saying, oh, I already have the value, and I want to create already resolved for a promise. So it's done already. So when we are calling then here, we are not waiting for promise. This promise is already resolved. So and so what I want to show is this then is our functor map. And of course, I'm displaying the promise and not the result. So, and this then here is our monad flat map. And it's in JavaScript, this is not visible. So let's first resolve both of the promises. Rafael, it's all, right?
Yeah, I guess.
And the result should be exactly this array, but a result after promise after promise completes. And we know that it's completing without errors. So yeah. So this result is also array inside the promise. So we need to map over and display it inside log. But sometimes
I think that promise.all is again a promise.
Yes, and I'm mapping over. Oh, but I don't have map. I need to write them. So this is also, we are using a functor map here. And we have, here we have result. So even in TypeScript or JavaScript, we are using the same logic or the same constructions, but we are not calling this in the same way. It's not really immediately obvious, but you can see here that this then is accepting function like a normal function, which is not result is not inside the promise also. And in this case, we are using function that is promise function, that returning the result inside promise. This is what async means. And in JavaScript, both of these abstractions of functor and monad are expressed in the same name of the function. And this then is both is functor and it's a monad. Rafael, is this helps?
Yeah, I understand. Yes, so yes, a promise in the resolution of a promise, you can return a promise or a flat value.
Yes, and now we know what is happening. It's really this implementation for a promise or for map and flat map. This is what is driving this the whole story about monad and functor. So this is why we can say, oh, promise is functor and also a monad, because we have this then operation on promise that accepts this normal function and also this is called monadic function, because we are returning this box on which we are already operating.
Well, good. Thank you, Tomislav.
And for the next time, we can see how different languages are giving support for this flat map operation. Because in Scala, this flat map. So if we have some function, we can write this for comprehension to get the value. So we can use our opt2 and we can return v here. And here we are using flat map. So the next time we can see how and why we have this support in our languages for this monadic operation.
What would make the monad a monoid?
This is just syntactic magic. Because if you have multiple operations like this, so we have v1, v2, right, and then I don't know, you will write something like this.
But I mean, what would make it a monoid?
So
trying to make a distinction. We defined a monad, and is the monad a monoid?
not directly, but they have this similarity. What Greg is comparing. They are like they are creating some kind of sequence. There it is.
Oops.
There is some kind of plus operation. So Greg is comparing this plus on monoid in the same way as we have a flat map for a monad. So we can say that with monad we also constructing some sequence in the same way as we are constructing this sequence in with monoid. So we can definitely for the next time or time after that we can compare this and see what are the operation of monoid. How can we implement monoid? Because monoid is a little simpler, but is not used that much in like regular programming. So the monad is used in like many places or like always, but monad is not so much used. At least not directly, because yeah, I will stop here and yeah, I'll leave something for next time. Yeah.
Yeah. Very good. Well,
This
hey,
reminds
these
me a
are.
bit.
So,
Go ahead, Natsu.
Is that somehow related to generic type Java?
sorry, you break it up a little. Can you repeat, please?
All this reminds me a bit generic types in Java. So
Yes.
you can make the same kind of inheritance.
Last time I was explaining this this difference between, or not really difference, but different notions of generics or polymorphism. So I started from dynamically typed languages and then slowly how this generics was included, right? So generics means we have this type level variable, and another step into this direction is to define this generic type as this type level variable as a function, and this is higher kind types. So here I didn't want to go to higher kind types. I was just using generics. So as you said, in Java we have generics, and I was using here just the generics.
Okay.
I'm not sure if I answered your question, but yeah.
Yes. I need to revisit the last lesson.
Cool. Yeah, and I'm planning to go back to this part of you know, this part of the abstraction and try to relate this with monad and monoids and all the other stuff. So I'm not thinking, I said what I wanted to say, and you know, this is over, because all of this stuff is like very closely related. So I want to talk about this, you know, in every session, you know, how this relates, because I think that understanding this part of, you know, programming, you can understand any language, right? You can just say, oh, what is the syntax you have for monadic operation? What you have for a function? Do you have a type level variable? What kind of variable you can have? and you can inspect any language and you can find out what can you do with this language. So, you know, it's just a different syntax, but if you know how to ask right questions, you can really learn any language in one day.
That is awesome. Very useful session.
Thanks. And then especially if we go to Greg's latest research and the paper, right? We can go even further and we can define the languages, how they're working with rewrite rules. So this is like the most interesting part.
Good. Well, hopefully it's all slowly coming together for us. This is all good stuff. So it sounds like we have an agenda. So we have some topics for next week.
Yeah.
Okay.
Maybe not completely specific, but yeah.
But so
if you have, yeah, if you have something, some part that I explain more in detail, please let me know. And yeah.
Yes. So everyone who's listening, who's on the attending now, or who's watching the video in YouTube video replay, feel free to go into the education channel in Discord and ask any questions or any topics you'd like to see elaborated on for next week's education session. Very good. Jim stepped away from his desk, but I'll get back with him, Tomislav, to have him provide you access to the channel. So for any supporting links and resources, we'll be able to include those in the description. And also, I just wanted to point out, so there is a RChain Education session playlist. So you can go and find the playlist in YouTube and go back and watch all of the previous education series. And with each particular video in the description section, there's supporting resources, links, and so forth to provide some further information on specific topics. So yeah, and once again, thanks Tomislav for putting together all those resources and supporting information for each video. That's, you know, I think the power of video is, you know, this is here for, you know, in perpetuity. You know, a year from now, 2 years from now, either us or, you know, new people coming on will be able to go watch these videos, you know, in the future and learn from them. You know, there's a permanent record to be always available. So this is great. Okay.
I want to say thanks for listening, and I hope that you know, I will make like a better explanation for. so this is also for me a very good input to, you know.
You know, there's the saying that the best way to learn is to teach. So, you know, I'm sure you're getting as much value out of teaching us about all these concepts, learning and getting a greater insight and a deeper understanding of the topics that you're teaching us. So it's, you know, everyone is benefiting from all of this. So great. So we're a little bit past the hour, so we'll go ahead and end it for today, and then I'll post the video later on today, and I'll see everyone back here next week. So thank you, everyone.
Thanks.
Enjoy your week.
Bye-bye.
Thanks.